Yeah. So from a physics perspective, uh, I think a lot of physics people will kind of be glib about it. Say, oh well, entropy will cause everything to fall apart, and that's true unless you put enough energy into the system, right? And then I would think that you can fix it, right? I mean, that's kind of the same thing as you can think of it like a house falling down. So say you have this brick house, and over time the mortar starts to decay, and the bricks start to fall off because of gravity and fall apart. Um, but you can keep fixing the house. Like you can keep putting in energy, and you can keep rebuilding the house and keep putting it back where it is. And I think that's kind of where longevity science is we're trying to figure out how to relay the bricks.
So hello and welcome to the Sheekey Science Show, where in this video I spoke with Loyd Waites, a particle physics PhD student at MIT who also hosts the Xapiens at MIT podcast and has interviewed Nobel Prize winners, legendary scientists, and recently even myself. Today we spoke about the fundamental components of the universe, dark matter to medical theranostics to discussing why we age. I hope you enjoy our conversation. So, hi Loyd, thank you for joining me today and welcome to the Sheekey Science Show. It's great to have you on.
Yeah, thanks for having me on, Eleanor. I'm flattered and happy.
That's good to hear. So, it's interesting to have you on the channel, obviously, because I've got a biochemistry background, whereas you do physics. And whilst I did physics a long time ago, well, actually, maybe not that long ago for me, it feels like a long time ago now. There's a lot of concepts and fundamentals I feel like I've either forgotten or maybe don't appreciate so much that could still be beneficial for the work that I do today. And more broadly, thinking about some of the changes that are coming in the world, every day and in the future. So I guess my first question is, what got you interested in physics? And how did you end up where you are right now? Well, not literally, but doing a PhD at MIT.
Yeah, so what got me kind of interested in physics in the first place were two things. I guess what kind of got me interested in science broadly were um, well, the first thing was fiction, right? So my mom actually started me into Star Trek at a young age, and when I was little, I would watch Spock and how he was obsessed with logic, and somehow I was kind of like that makes sense, and in kind of an ironic way, logic makes sense. Um, but I always kind of looked up to him for some reason, and he was the science officer, and that kind of drew me into science. And then, um, kind of a kind of a funny story. When I got a little bit older, when I was in like middle school, I was watching cartoons all the time, like a kid would. And then I got to the age where I was like too old to be watching cartoons, and then people started making fun of me. So I said, "Fine, I'm not going to watch cartoons anymore. I'll watch something else." So I like scrolled up to the next couple channels, and it was the Discovery Channel and the Science Channel and the History Channel. And I was like, "You can't make fun of me now. I watch documentaries all the time," and I was in for a rude awakening when I realized what that meant. but uh, and that was back when Discovery was really about like science and stuff. And so there were a lot of great shows on there with like the old Michio Kaku shows, and this was probably before Neil deGrasse Tyson even got super in the public eye. Brian Cox was another one who works at CERN now. Maybe I should try and find some random people I know at CERN who might run into him or something. But those shows were like very heavy physics and astronomy focused. They were very much like trying to understand theories of everything, trying to understand how the universe works and why planets and whatnot were behaving the way they were. And I always thought that was the coolest thing ever. And so I kind of when I was going into undergraduate, I wanted to be an astrophysicist because I thought like I had the kind of noble picture of Galileo looking through his telescope, looking at all of the planets and whatnot, and like all the beautiful pictures of the Hubble Space Telescope. And I wanted to do theory. I wanted to try and understand these kind of theories of everything, these deep layers of how the universe works and explaining exactly where that comes from. And so I thought astrophysics was the way to do that, and as I got older, I realized it wasn't really. It was more actually in the particle physics realm. And then once I became a grad student in particle physics, my opinions on that have changed on how exactly that works. Um, but that was kind of my path on how I got there, and it was also very much that like it was kind of solidified by the idea that physics is fundamental. Like physics is kind of at the bottom, right? Like physics describes describes like electrodynamics. Electrodynamics, you can kind of wiggle your way into getting into chemistry through that part, and then through chemistry you get to biochemistry. Biochemistry builds up life. And so when I was young and naive, I had this idea that like uh, from the standard model you could build up and understand all the laws of biology, right? Like obviously that's not very feasible, but like that was kind of the idea. And it was kind of like if you had a big enough computer, you could figure it all out just by this one super powerful equation that you ran long enough, and then you could kind of figure everything else out after, and everything else is kind of an afterthought. So that was what really solidified me in physics. um, and that path has kind of changed as my opinions about kind of reality have changed and have set in as I've gotten older. But that was how I got there.
So you mentioned that, like, obviously now you're doing particle physics in your PhD research, and so my audience probably are less familiar with these concepts. And so, what are the kind of the fundamentals, as you say, to understand what is particle physics and what exactly is it that you're studying?
Yeah. So the spiel that I usually give is, so imagine in physics the kind of ultimate goal, right? It is this theory of everything. It's this single unified theory that what I was talking about. You start from the bottom and it goes all the way up, and you have a strong enough computer to run everything, and can hypothetically predict the future with this ultimate equation. And the secret of physics is that we actually have one, right? It's called the standard model. People don't refer to it like that because there's a lot of problems with it. Um, but the standard model, as far as we know, does do a very strong description of electrodynamics, of the strong and weak nuclear forces, uh, but it doesn't have gravity, which seems kind of silly, right? Like gravity is one of the most obvious ones. Like if the standard model was the only thing, then like stuff wouldn't fall to the ground, and I wouldn't be sitting here. Um, but I mean, 3 out of 4 is not bad. That's a pretty good theory. Um, Having gravity involved is what a lot of theoretical physicists are working on now and trying to make a unified theory. Um, but there are also several other very large jarring holes. One being dark matter. Dark matter is seen by astrophysical observations to make up, I want to say 22% of the universe, but the precise um, calculations change, or the estimates change. And then there's dark energy, which a lot of people don't even really think about. There aren't a whole lot of ideas about it. That explains the universal expansion. Um, and so the majority of the universe, we have no idea what it is, and that doesn't really fit into a very good theory of everything that's being used to predict the future. Um, Another one, which is kind of a low hanging fruit, I think, is neutrinos. So there's a list of fundamental particles. Typically, you might think of atoms, but atoms are actually made up of neutrons and protons and electrons. And then within the protons and neutrons, there are quarks that spin around. And you can see this chart, which is called this, which comes up in the standard model, that describes a list of all of these fundamental particles. And one of the more interesting fundamental particles, I think, is the neutrino. There's more of them than there are protons and neutrons by like hundreds of orders of magnitude. It's the most plentiful particle in the universe, and it doesn't interact with anything. So there's always the quote of, there are millions going through your fingernail every second, right? But you don't feel any bump on your fingernail because the cross section is so small. So neutrinos were actually thought to be dark matter for a while, but when the estimates came out of how many neutrinos there were and what their approximate masses could be, they were eliminated as potential dark matter candidates. I think they eliminated a small fraction of what the dark matter was described to be, but not nearly enough. The thing is, in the standard model, neutrinos are described to be completely massless. Neutrinos move almost at the speed of light. If they moved at the speed of light, they would have to be massless, like a photon. That's kind of a fun sidebar, is that the speed of light is not actually just the speed of light. It's a fundamental constant of speed. And so like if you have any massless particle, it will move at the speed of light. So I think in Russian, they don't call it the speed of light. They call it like the fundamental speed
Oh,
or something.
interesting.
And that's why it's always denoted C and not actually denoted as the speed of light. Yeah. Um, Light just happens to be a massless particle that we interact with on a daily basis, and so we call it the speed of light. You could also say it's like the speed at which information can possibly travel. But anyway, so a long time people thought that neutrinos traveled at the speed of light, but they found out, one, that they don't move precisely at the speed of light, and two, that they change their flavor or their state. So if you think of, there are three different types of neutrinos. You have your electron neutrino, which couples to your electron and has a matching lepton number to the electron. You have your muon neutrino, which matches obviously your muon and your tau neutrino. And if, say, electron neutrinos are produced in the sun, which is pretty common because of the nuclear reactions that occur in the sun, and then they travel to the Earth, you'll notice that you won't get the right number of neutrinos detected that you should based on many of the solar models. It was off by a factor of 3, actually. And part of the reason why was they realized that these neutrinos are changing from one to another as they travel. This has to do with, it's a little bit in the weeds, but basically it's because there are two possible descriptions of a neutrino. That one is describing a neutrino when it's moving, and one is describing a neutrino when it interacts. And each of these states are actually superpositions of the other. So when you have a neutrino moving, it exists in this superposition. It's not any of these three interacting states. It is simultaneously an electron neutrino, a muon neutrino, and a tau neutrino, all at the same time as it's moving. But when it interacts, it can only interact as one of these three things.
I see. Okay.
Like classic quantum mechanics, mind-bending nonsense. But this is like the concept of quantum superposition, that you have three different states that exist. You have one state that exists as a superposition of three other states, and similarly the other way around. If something interacts or is produced as an electron neutrino, it exists as a superposition of these three other neutrinos. Yeah. So that meant because they had a mass eigenstate and they had these flavor eigenstates, and you can see that they're changing. In order for it to exist in an electron flavored neutrino state, it would have to exist as three different mass eigenstates to make up that superposition. But in order to have three different mass eigenstates, they had to have mass, because those masses had to be different from each other. Therefore, neutrinos were not massless, and the standard model had an inconsistency in it.
Ah, okay.
Yep. So from there, the neutrinos therefore needed to have mass, and that ended up winning a Nobel Prize. And so from there, kind of a whole bunch of neutrino physics has fallen out. I mean, the obvious question is, well, how much is that mass? And so that's some of the people. Joe Formaggio, who's on my hallway, he works on a couple of experiments trying to understand specifically what this mass is. But there are some other things that come out into the math that, if you look at it closely, you'll see that in order for them to have mass, they also need to have a right-handed counterpart. They need to have a separate type of neutrino called a sterile neutrino. And there have been hints to this in experimental data. And so that's actually what I work on. And it's kind of a long, convoluted way to get there. But so what I work on primarily is to make, because neutrinos are so hard to detect, because there's so many going through your fingernail at every given moment. Instead of producing larger and larger detectors, which is the kind of the main use of what's going on now, or making very, very dense detectors that take advantage of different scattering techniques, my group works on an accelerator-based neutrino to make this kind of neutrino floodlight, right? So instead of making a huge detector to be in some mine somewhere, you have an accelerator that creates this massive amount of neutrinos right next to the detector, and you could say, okay, any signal that comes from this is specifically from this source, and you can do all the neutrino physics you want because you have so many neutrinos.
Cool. So you basically just answered the questions I was gonna ask you next, anyway. So why is it they don't interact with anything, these neutrinos? So what is it you're actually detecting, and how does that process work? And sort of on from that, maybe a sort of dumb question: what is the role of these neutrinos? You say that everywhere. So why are they getting produced, and how do they influence things that go on in the universe?
So some oral exam questions here. So you don't actually observe the neutrino physically, right? Like at the end of the day, what we're actually observing, and this is kind of an important nuance in all kinds of physics, is what we're actually observing is almost always light, right? And so what we observe in the detectors that I work with is something called inverse beta decay. So the neutrino comes in and interacts with a particle inside the detector, which emits a flash of light, and then can also cause, there's a second signal that gets emitted that emits a second flash of light and cascades and whatnot. The process is a little bit technical, and there's diagrams that will explain it better than my hand waving. But it's called inverse beta decay and produces these flashes of light that are then picked up by photomultiplier tubes surrounding the detector. And from there, you can say, okay, there have been these many flashes of light, and that means we have detected these many neutrinos. And sometimes people can get creative with saying, okay, based on the detection times of where these different photodetectors found the light, you can figure out actually where within the detector it was set off. And depending on how bright the light was, sometimes you can understand the energy resolution as well.
Okay, I see. And so what is it that you do, like what was your day-to-day like during your PhD? And you talk about researching these sterile neutrinos, but previously they were thought not to exist. So how did you find their existence? And then what kind of discoveries have you made in your research so far?
Okay, so to be clear, I haven't discovered anything. No one has discovered sterile neutrinos, and my project still isn't built yet. This is I do a lot of design work, and honestly, on the sterile neutrino side, that doesn't actually take up most of my day to day. The majority of my day to day is depending on what project I'm on. So I would say the majority is actually designing this accelerator. So the idea is to we're making this neutrino floodlight. This is a work in progress. This isn't something that has been built yet. This is proposed. Um, and the majority of my day to day is writing code that does beam dynamic simulations, actually. So I'm designing all of these magnets and electrode systems that shape and steer a beam so that it collides with a target so that it can produce these neutrinos. We talk about the neutrinos because it's the end result, but a lot of the hard work is actually involved in making the system that makes it work. um, so my day to day is typically split between two things. It's either working on these specific beam dynamic simulations, or sometimes it's phenomenological work. Like the axion work that I've done was finding cross-section estimates of expected event rates of what these axions would be doing inside this detector, and then say, okay, based on a certain amount of flux in our beam, connecting that to how many actual events we can see in our detector, so that we can do an analysis once the experiment is up and running. Or more kind of importantly, in a proposal, say, okay, if we build this experiment, what are we going to be able to see? And I can say, okay, based on these calculations, we will be able to see this with this signal and this confidence level, and we'll be able to rule out like these experiments and whatnot. So I haven't discovered any of these things, but hopefully in like 5 to 10 years when this thing is built, they'll go back on my analysis and they'll say, okay, these are the exclusions that we are expecting to see. And then based on that, we can say, oh, well, we looked in this region, there's a signal here, and oh, there's the sterile neutrino, or oh, there's the axion.
Oh, I see. And so you've mentioned now a couple of times these axions, but would you be able to elaborate on what exactly these are?
Sure. So I mentioned earlier that one of the glaring holes in physics was dark matter. That there is how dark matter came about. I know when I was first learning about dark matter, I didn't have an idea of kind of what it meant or where it came from. So I thought a lot of the time you'll see sci-fi movies or whatever that'll say like, oh, we have these dark matter particles, and the reason why it's called dark matter is because we don't know what it is. All we know is there are these strange gravitational anomalies that we see in space. One of the first ones was if you look at the speed at which galaxies rotate, they should actually spin apart, and all of the stars and whatnot should be spinning out into the galaxy, or not into the galaxy, into the cosmos, I guess, and specifically not be in the galaxy because of the centrifugal force. But that doesn't happen. It gets held together because there's some amount of mass that seems to be invisible within these galaxy clusters. And sometimes when people see that, including me, when I first looked at it, I was saying, well, maybe people are just kind of doing their calculations wrong, and maybe there's a modified gravity theory that should be put in place to look at this. So I think the most important piece of evidence is the bullet cluster and gravitational lensing. That I don't think when you go to dark matter talks, you see it a lot, but a lot of the time you won't see it outside of that. And basically, what it was is you have two clouds of gas, right? So these two clouds of gas over time, because they all have mass, they'll run into each other and they'll collide. and the two clouds of gas, because their gas will kind of bump into each other and they'll slow down. They'll kind of just blob up, right? Imagine if these clouds also had a large amount of dark matter inside of these clouds. Well, dark matter doesn't interact electromagnetically, which means it physically cannot bump into each other. Whenever two dark matter particles, we don't know what they are, but we know that they don't interact electromagnetically, and so they can't bump into each other. And so whenever two dark matter particles bump into each other, they just fly right past each other. And when we look at the bullet cluster, which is these two gas clouds going into each other, we see that. We see these gas clouds kind of stopping, but if you look at the gravitational lensing, which is, you can say, is like telescoping for mass, right? If you look at the actual mass distribution of the gravity distribution, it's predominantly focused outside of the gas clouds. So the gas clouds center in the middle, and then there's these two blobs of basically particles that have just like passed right through each other and didn't bump into each other and didn't get stuck. And so that would indicate like there's something making these large mass pockets that is not interacting with our telescopes, but is creating a very large amount of mass. And so I think that's really the smoking gun for dark matter. And so I don't know any kind of theory that can describe that. There are some interesting modified gravity theories that have tried to approach it, but I haven't heard any really take off.
Okay.
Yeah. So what are axions, and what do axions have to do with this? So there were a bunch of different dark matter candidates that have come out. Sterile neutrinos were actually one as well, because they don't interact at all. They wouldn't bump into each other, but they also don't have, and they might have a lot of mass. But it depends on, there's different ways to kind of play with it and tune the parameters to decide whether or not they'd be dark matter. But one of the more compelling ones was something called an axion. And the reason why I think it's so compelling is because it originally was not proposed as a dark matter candidate. It was kind of found as a dark matter candidate by accident. This gets into another deep in the weeds particle physics problem, but there's three fundamental symmetries in nature. That is charge symmetry, parity, and time symmetry. And essentially what it is that, if imagine you have some particle, if you reverse all three of these symmetries, your charge, your parity, and your time, then everything should interact exactly the same. Meaning, like, say you have an electron, it might take a second to think about this. It took me a while. It took me probably a couple months to really understand this. But say you have an electron moving in this direction, right? It has a negative charge and it's moving in this direction, and it pulls on whatever around it in that way. That should be identical to a positron or an anti-electron moving the opposite way in that time, right? Because instead of pulling all of these objects in that direction forward in time, it's now pushing all of the objects away backwards in time. So the interaction between these two things should be completely identical. That's kind of a weird mathy thing to think about, but it's basically that if you flip everything should behave the same in reverse that it does.
All right, so you mean like a mirror image, or like if we literally just like stop the clock and we turn back time, things would happen the same, or what? Is that quite right?
Sort of. So a mirror image is one of them. Parity is another word for a mirror image. So that has to do with like chirality, right? Chirality in chemistry is the same idea that you have these two parts that even if you flip them around, if you flip them in a mirror, they will become physically different. So that's the first one. That's parity. The second one is charge. So all of your electrons are now positrons. The electrons now have positive mass instead of a negative mass. And so they will push instead of pull in whatever direction. And the third one is running time in reverse. So if you do all three of these things, instead of having the electron moving this way, or say the electron is moving this way, and you have another charge here. You have an electron. So normally two electrons would repel each other, and so this one gets pushed away. If you run it in reverse and you change this charge, this is now a positron, and time is running in reverse. So what should happen is it should still get pushed away, even if this is an electron, because it would be getting pulled because its opposite charges attract, but it's in reverse, so that means it gets pushed away because time is reversed as well.
Okay, yeah, okay, I got it.
Yeah. So that's called CPT symmetry, and that's in a lot of theory papers. And I think it's a kind of an important fundamental idea in particle physics. But that's a lot of it. it gets deep down into the experiments because of things like CP symmetry. And what CP symmetry is every once in a while you can break off two of these symmetries. So instead of having CPT, which is always conserved, you can actually break these symmetries individually. One of them being charge parity symmetry. So if you change the charge and you change the chirality of the particle, there is an expectation that sometimes that symmetry should be broken. And what was found is in the strong force, which is one of the four fundamental forces that I described before, it has never been observed experimentally, which is weird. It's possible because there's a parameter in the standard model that could just be super small. It's possible that this CP symmetry is just very unlikely to be seen, and that's why we've never seen it. But it seems weird that it's almost exactly zero. And so what was proposed of this was two people named Petchy and Quinn proposed a additional symmetry that could be broken to make it so that this term would always be zero and that the strong force never violated the CP symmetry. And that would correspond with our experimental observations. And then Frank Wilczek and Steven Weinberg simultaneously looked at this paper by Petchy and Quinn and realized that in the case of the symmetry breaking, there would actually have to be a new particle that would be a result, which would be this experimental observable. And that would be the axion. And so that's where it came from, the SOAP cleaning up the strong CP problem. The strong CP problem being that we never actually observe this CP violation, this CP symmetry violation in the strong force. And so to clean up that problem, you add an additional particle, which is the axion. And Frank Wilczek said, well, I wanted to name a particle after the axion SOAP since I was a little kid. And so now he has produced these axions. And when they discovered this, or well, they didn't discover it, but they came up with this theory. They kind of looked at what the different possible parameters were and what the masses would be compared to some of its couplings. And they saw that in some cases where the masses, especially when the masses were sufficiently low, and in certain cases where the masses were higher, that the axion could actually describe the dark matter phenomenons that we've been seeing. And so it was this very serendipitous, like, oh wow, here's this interesting kind of pet project that we found to understand these experimental observations. It could actually be way more than that. And since then, axion experiments have kind of exploded, and there are all kinds of different axion experiments looking in different places and looking for them at different masses and different sizes and different couplings.
Well, it seems interesting, right? Because as you
so
say, it seems to be solving both what is dark matter, but also solving this CPT problem, right?
Right. Yeah. So that's why a lot of people have kind of moved over to axions from other potential dark matter experiments, is because it simultaneously solves more than one problem. And so wouldn't it be really great if someone found it and then all of a sudden these problems were resolved?
So you think you have found it, or is it still just theoretical observations?
No. I haven't found the axion. I would be on my way to Stockholm if I found the axion. No, so the paper that I just put on arXiv is about our neutrino experiment, actually. It's our accelerator-based neutrino experiment next to a big neutrino detector. And we said, well, in addition to that, you can actually produce, instead of just producing axions, it's actually possible to produce, instead of just producing neutrinos, it's also possible to produce axions in this target. And when you produce axions and you're next to this big neutrino detector, you can actually try and pick up an axion signal and do a detection. How that's done is a little bit funky. It's like people describe it as light shining through a wall, but I can go into detail if you want, or I can just say that there are ways to detect axions in a neutrino detector. We can leave it at that.
Well, I guess so. Like the interesting questions are obviously why we study particle physics is so that we can address like how did the universe get created, understand dark matter, and how the kind of like the big fundamental questions about life. But in terms of more day-to-day use cases, I know that there's a lot of overlap between using particle physics for medical imaging. So what potential use does your research have in that area?
Yeah, so I said most of the time I'm actually spending working on beam dynamics. And when you talk about using ion beams. The majority of ion beams aren't used for particle physics experiments. I was kind of sucked into that by joining the particle physics division at MIT. What the majority of them are actually used for is to produce medical isotopes. So if you go to a hospital and you say you're getting a PET scan, right? And when you go to get a PET scan, you have some injection put into your arm, and then they put you in a scanner, and then they look at whatever tumors or whatever the tag is, depending on what tracer they put on the PET isotope. And what that actually means is they are injecting you with a small molecule that is attached to a radioactive isotope that was produced sometimes on site, depending on what kind of isotope it was, or sometimes very far away, and it was made by this massive accelerator. And because we're making this massive accelerator for a neutrino experiment, this massive accelerator is actually possible. It also makes it possible to make far more of these really exciting isotopes. So in the case of a PET scan, what happens is this radioactive isotope attaches itself to the tracer attaches itself to a tumor, and then it undergoes a decay. And that radioactive decay emits a positron. The positron annihilates with the electrons in your system and produces, again, light. So your body's acting like a kind of like a little mini detector, right? And then outside of it, you have these scanners which actually pick up the light signals from these annihilation signals.
Yeah, so
And
sorry
so
to
that's
interrupt, but
a
my
fundamental.
basic understanding of the PET scans was, so it's the glucose that they inject, right? So the idea the tumors, they're more metabolically active, so PET scans work by it kind of lighting up and highlighting what the tumor is.
Right. So it varies a lot. Like I've even heard of attaching radioisotopes to neurotransmitters, which I thought was, I don't know, a little scary, but also like makes a lot of sense, right? If you're trying to do brain imaging. But yeah, so in the case of tumors, what they do is they've attached radioisotopes to glucose. The cancer sucks up all of the glucose because it's a glucose hog, and then the isotope, once it's inside the tumor, undergoes a decay. And then that's kind of, I work with producing the isotope, not actually the tracer. So I don't know a whole lot about the tracers themselves. I just know that like you want to make your different isotopes chemically similar in order to use the same tracers. But essentially, yeah, it gets gobbled up by the tumor and it emits this positron, which is why it's called PET scanning. It's positron emission tomography. It's like fundamentally using antimatter to like find tumors. Like that's pretty cool. And so it's using the property again of actually CPT symmetry a little bit, that you have this annihilation that happens with a positron bumps into electrons because there's electrons all over your body in all of the different cells, and that causes an annihilation which produces two photons, and then the two photons actually just kind of like radiate and bounce around and produce enough light that can be picked up by a signal, by an outside detector and a PET scanner. But some of the other stuff that I think is even more interesting is you can use like a similar idea. So PET scans are like something that a lot of people are familiar with, but you can also use them for therapy and for theranostics. So there's a lot of push in the nuclear medicine community to simultaneously do diagnostic treatments and therapy treatments. So having a single isotope or a single pair of isotopes that you can, instead of injecting someone with one isotope, trying to do some kind of therapy, and then injecting them again later on and seeing if the therapy's working, you can actually do it simultaneously with certain types of isotopes that both emit a positron for PET scanning, but also physically kill the tumor. And so you can watch the tumor get killed as the nuclear medicine treatment kind of takes hold.
Oh, that's super interesting.
So that's yeah. So that's one push. I have a paper talking about that too. But so there's one of the therapies that I think is super exciting are called alpha emitters, specifically actinium-225. And I'm not sure if I can share the image or not, but there's this study from several years ago that essentially showed a malignant tumor through a person's body, and there were little black spots all over them, right? And so this is essentially a dead man walking, right? And that's what allowed them to do this clinical trial. And so what they did is they had actinium-225, which emits 4 alpha particles, and alpha particles are a helium nucleus, right? And so these helium nuclei get emitted in radioactive decay, but the good thing about alpha particles is they're large. I mean, large on like an atomic level. They're still atoms, but they're large enough that they actually think of them kind of like a bowling ball. They just like kind of run through everything and stop because they lose all of their energy, but in a very small area. And so that's perfect for if you're putting them right next to a tumor. So if, I mean, very basically, you could imagine like, okay, I'm going to inject these alpha emitters into a tumor. Well, then they're going to emit all of their alphas. Actinium-225 has like a 4 alpha chain that kills everything over 50 micrometer radius. Everything in that 50 micrometer radius is going to be destroyed. And there's not really anything you can do about that. It's not like a lot of therapies where it's kind of like, oh, the uptake efficiency wasn't enough or something like that. It's you're literally nuking the cell, right, with a treatment like this. But you're not going to be able to inject it into tumors all the time. So what you're really doing is you're attaching one of these things to a tracer, say glucose, for example, and then it finds it, attaches itself into the tumor, and then undergoes this radioactive decay and kills everything in that region. And the results of this are amazing. I looked at this picture and I was like, "That's it. We cured cancer." like
Put me out of a job.
we've yeah, but it's crazy looking at these images because they took someone who was just like cancer spread all over their body and it was gone within 9 months. They were cancer free in 9 months because they literally just like nuked all of the individual tumors by attaching them to tracers.
And was there any, because obviously, I mean, I know that the cancer, the tumorous cells are more likely to take up the tracer, but is there also any implications for the killing of like neighboring healthy cells?
Yeah, so the first thing is you have to make sure like the half-life is sufficiently long. You need to make sure it has a sufficiently long half-life, so that it's not just like exploding everywhere in your body, right? Because you don't want to kill all the neighboring cells. The other good thing is it's only 50 micrometers, so it's pretty localized. You won't have like you're not going to end up with cells that are in the region unless you're dealing with something that needs to be super localized. Like I don't know if this could be used on something like brain tumors. I don't know if I would trust that, but I think there are other people that there might be people working on that. I'm not. A lot of the innovation now is done in two places. One is where I work and trying to produce more of it, and the other is in the tracers. And producing the tracers is certainly non-trivial, but it's not something that I'm an expert in. So you need to kind of make sure that your tracers are actually being uptaked by the tumor and not latching onto anything else. But there's something I can do to help with that actually, and that goes back to Theranostics. So last year there was a paper put out by the Department of Energy. So actinium-225 is kind of my go-to example of an alpha treatment. But if you want to see how the alpha treatment is doing, you need to do other types of imaging to see how the tumor is progressing. And you're not 100% sure where the alpha tracers are always ending up, right? Because you're not actually imaging the alpha tracers, you're imaging the tracers of whatever PET imager or spec imager that you're using. But last year, the Department of Energy put out a paper using a new PET isotope called cerium-134 that was actually chemically almost identical to actinium-225. So you could use any tracer that would be attached to actinium-225 and use it in cerium-134. And that there was another one. There was a thorium isotope as well that they used for an alpha treatment. So you could have a single tracer that chemically attaches to the actinium-225 and to the cerium. And so because the cerium just acts as an imaging agent, you can see exactly where all of the tracers go. And so you don't have to worry if the actinium is getting stuck in someone's knee or something random like that. You would always be able to see through the PET imaging exactly where those tracers are going. And so if you did them simultaneously, not only would you be able to watch to see like how the tumor is progressing over time with the same tracer, but you'd also be able to ensure the safety of the alpha emitter.
Yeah, wow, this is really interesting technology. I kind of want to read more into it now that you've mentioned it. I guess as well there's been mouse studies, or did they go straight for the human patients?
So in cerium, I think it's just been mice. I've only seen a mouse paper. I wouldn't be surprised if since then they've done like a clinical study, but I know there are clinical trials going on with actinium-225. The other thing with actinium-225, I know in terms of like the approval status, is typically when it's approved as a drug, it's not just approving the isotope; it's approving the isotope and the tracer and like the full system. And so, if you want to have one for pancreatic cancer, you want to have one for this type of cancer. It's each is a separate individual treatment that needs to go through a separate approval process, which makes sense, right? Like you don't want to have a bad tracer no matter how good the isotope is.
I mean, you got me thinking. So the idea is obviously, if you have a good tracer, then the technology is already there. That if you wanted to target a specific population of cells, you could do it using this technology.
Yeah, so I even heard one person was using it to treat like fungus, like a person's fungus, because it was just like it was able to just like kill everything in the region. So they had like, I think they had like some kind of actinium cream that they put on a fungus to kill it. But yeah, I mean it's looked into for tumors, but it's not exclusive for that by any means. I'd be curious to see if some bio people out there might be like, oh, well, this is perfect for like cell death in this.
Well, I was going to say senescence,
like,
right? I mean, if you could find some kind of tracer that's taken up by, a population of senescent cells, maybe it's the first.
Well, that could be interesting. Could you do an alpha therapy on all senescent cells? I feel like you could, but it might not be.
Yeah, no, I mean, I mean, that takes us a whole into this analytics field and talking about senescent cells, but we're here to talk about your research, not my research. So I'm going to stop talking.
Well, so like, I like the actual roadblock there. I think that's a really interesting idea because I think the actual roadblock there wouldn't be. I mean, if you're a biologist and you can magically be like, okay, this is the senescent cell. Like, here's the tracer. Put your radioisotope on it. I think you could do that. But what I'd be worried about is I feel like senescent cells are probably like spread evenly throughout your body, right? Is that a
so we
assumption?
don't really know, but yeah, they all see clusters, so it depends on like the formation of them. But you're right. So if you're going to kill things in the radius of whatever diameter you said it was, so that would affect neighboring cells that potentially were still healthy, or like stem cells. So yeah, I get that.
Yeah, and I also. I mean, I don't think there's been any crossover between senescence and nuclear medicine yet, but I wouldn't be surprised if the neighboring cells, like right around that like 50 micrometer range, actually become senescent. Because maybe there's like I wouldn't be surprised if because all of these cells have literally just been nuked that like an inflammation signal. Or
so one of the, I mean, to again bottom of my stuff, not yours. In terms of therapeutics for cancer, a lot of them use chemotherapy, right, which is meant to just kill the tumor cells. But the caveat is that it also affects the surrounding healthy cells, which could enter senescence. And so you might clear the tumor cells, but you end up with senescent cells. Whereas this approach using nuclear physics, the idea is that you just you're only going to be killing you only kill the cells. It's not likely that you're going to cause a cell to enter senescence. Although I guess that's probably not been looked into yet.
I don't want to say that that's the case because I don't know. I don't think anyone does. I would be shocked if anyone has done a study looking at the senescence of like bordering cells after alpha therapy. But that's a great study that someone should do. That is not
for sure. No, that's it's super interesting. And so besides like medical imaging, then where else do you see the overlap with like particle physics, nuclear physics, and I guess like research in biology or just more generally in health research?
So I think there's more overlap than a lot of people give it credit for, because I remember when I was in undergraduate, there was my roommate and best friend that was a chemical engineer, and he was having problems with just like I think it was, I want to say it was graphene or something. And he was having trouble understanding like why some kind of molecule was stable when it had a delocalized setup of electrons on above and bottom. And in order to kind of understand that, it was easier for me to understand it because I had an idea of an electron wave function. So imagine if you have like a benzene ring, and you have your hydrogens up and down your benzene ring. And then you have all of your electrons, and you take an electron out, and it doesn't just like crumple, right? Like even if it has a single electron taken out, it doesn't just like fall apart. And I think part of that is because the electrons aren't physical dots, right? The electrons aren't these individual dots that are moving around in the benzene ring. They form this distribution. They are non-locally acting particles. Um, they exist in this literally this kind of like blur around the particle, which means their charge distribution is also in that same blur around the molecule. Um, and so I know some kind of physical chemists take advantage of knowledge like this to be able to have some funky tricks to be able to um, find new types of molecules and whatnot. I'm not an expert in that, but uh, I feel like I get a good intuition from biology sometimes because of my physics background. But I also think that it probably makes me a little cocky sometimes, where I look at it and I say, "Oh, this is just some like physical system, and like it does this," and I'm completely wrong. So I think there's some give and take.
Okay. In that case, I know that you're interested in longevity, which is how we first got connected. And so, from your physics perspective, what is aging and why are we aging?
So, I mean, I don't have a outside of like the hallmarks of aging that you see in a lot of papers and um, certain like theories of aging. I mean, the basic way that I always kind of assumed it was just entropy, right? And that's what a lot of people will consider. It's just the breaking down of cells over time, and the breaking down of genetic material over time, or epigenetic material, which I mean, entropy is I've said before that entropy is the greatest evil in the world because it's completely inevitable and it's kind of unstoppable and causes all of the negative things that we think about, right? So like aging, death, decay, destruction. It's all just because of entropy. Because the lower energy states, the kind of the macro states that you do not desire are the most probable because you only want a certain subset of things to exist, and if you only want that certain subset of things to exist, everything will fall away from that one subset because it's just like because there are more possible ways for the thing that you want to not exist than for it to exist, and so everything just kind of falls away from what you want. um, and so I think aging is a lot like that. It's like I want to continue in the shape that I am in, um, and that's just not possible because like I get dirty. I need nutrients to continue to survive. I need to continue to put energy into my system to be able to continue to exist at all, rather than not age. Um, but that actually kind of leads us to the next point: is aging truly inevitable? I mean, entropy in a closed system is completely inevitable. But I read this awesome quote out of one of David Sinclair's papers that is like entropy is inevitable, but but a living system is an open system, not a closed system. So you can continuously put energy in, and you should be able to reverse the aging process because we've seen that the aging process is reversed in other animals such as certain types of jellyfish. And then if you also clone a cell, you can see that you're able to have this have a new organism produced without any of this information actually being lost. Um, so there's something going on there biologically that I don't fully understand. Um, and it makes sense from a physics perspective that like if you continue to put energy into a system, you can kind of circumvent these ideas of entropy causing things to fall apart. Which makes me happy, right? Because I don't want to get old and I don't want to die, right?
Yeah, no, that's interesting.
So like yeah, so from a physics perspective, uh, I think a lot of physics people will kind of be glib about it. Say, oh well, entropy will cause everything to fall apart, and that's true unless you put enough energy into the system, right? And then I would think that you can fix it, right? I mean that's kind of the same thing as you can think of it like a house falling down. So say you have this brick house, and over time the mortar starts to decay and the bricks start to fall off because of gravity and fall apart. Um, but you can keep fixing the house. Like you can keep putting in energy and you can keep rebuilding the house and keep putting it back where it is. And I think that's kind of where longevity science is we're trying to figure out how to relay the bricks, and how to actually do
All
that.
right. Yeah.
And that's not a question I can answer, unfortunately.
Unfortunately, I can't either at the moment. But it's interesting that you say that because I also spoke last year with Andrew Still, who also wrote a book called Ageless. But his background initially was physics, which he did at Oxford, if I'm remembering correctly. So he had a similar like entropy was the reason. So it's always interesting to hear the different perspectives. And so obviously, as you're coming to the like near the end of
Actually, one more thing about entropy too. So something that's kind of interesting about uh, a lot of arguments about thermodynamics and entropy is that, I mean, at first order, people a lot of the time will assume that life shouldn't exist because of entropy, right? Because here are these very complicated systems that have kind of like grown out of nothing, right? But there is something to be said about the local increases in order compared to global decreases in disorder. And I think I heard an argument once that because life exists, using we are actually causing greater increases in entropy because we're like creating more heat because we're biological systems than if everything was just kind of sitting there.
Well, there's similar
Um,
arguments in
and
protein
so,
protein interactions that the water molecules they become more disordered as you bring two proteins together because the kind of circumference, like you basically block off the surface area. I don't know if that makes sense, but there's similar principles.
sorry, what do you
So if
mean?
you
So
have
there's
two monomers
with
of a protein that then dimerize,
mhm,
the exposed surface area decreases because they're now interacting together, and so the surrounding water molecules,
mhm.
um, there's less of them when they're dimerized as opposed to individual, and so the entropy it becomes more disordered. The water molecules, so we call it like
Okay, yeah, I
entropy-induced
see what you're saying.
dimerization.
Yeah, entropy is kind of a weird concept.
Especially when a biologist is trying to
I
explain
have a friend of mine who also
it.
makes a very good point about entropy. Is that he 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 will state very firmly that entropy doesn't exist, and he's actually kind of right. So how he describes entropy is he basically says, well, entropy is a description of how little you know about the system, which is true because hypothetically, if you were to, other than like the quantum measurement problem, which is something no one's really actually looking at, uh, you can have a say you have some perfectly deterministic system, even like a box of gas, right? And you had the perfect idea of where each of those particles were going. It's deterministic. You can understand where each of these things are going. But what you do when you calculate entropy is you say, okay, well, I don't know all of this information. I'm going to kind of make an educated guess about how this system works. And based on that, I'm going to say what is going towards disorder. But disorder is really just like kind of a description of the number of possible macro states. It's the number of possible orientations that each of these gases could be in. And you could say, okay, what is the probability that it's in like this particular macro state compared to this particular macro state? And then depending on how these different pieces change, you'll say it's either in a high or low entropy state. But that doesn't really mean anything. That's just kind of like how good is your educated guess. It's not like a physical property. It's just kind of I guess, a mathematical description, or even like an error in your mathematical description.
Yeah, interesting.
Yeah, I thought that was a cool take on entropy because it's like entropy is always like, oh, it is a fundamental truth and force of nature, but it's really not. It's just like how we look at
Well, so,
systems.
yeah, speaking of fundamental truths, so what are the kind of unanswered questions that you feel are in the physics space at the moment? And yeah, what does the kind of next 5 years, 10 years look like? And what sort of findings do you think we'll make in this time frame?
So I think in terms of particle physics, I think the main unanswered questions are basically how do we fix the standard model? How do we find these? How do we fill these gaps that we've talked about? What is dark matter? Why is the universe expanding at an accelerating rate? What is the neutrino mass? Are there additional neutrinos because of this additional neutrino mass? What are their properties? And is it possible that there is some additional theory that could be unifying these things? I remember on your question sheet that you actually had like a what is kind of the hope of a theory of everything or a grand unified theory. And a lot of people think that it's just never going to happen, including Frank Wilczek. Actually, when I interviewed him, he's specifically said that he doesn't think there's a theory of everything. He doesn't think it's going to be that clean, and it kind of makes sense. Like a lot of people have been searching for this unification for um, for the three forces that we've unified in the standard model and gravity, but like there doesn't have to be one, right? Like it doesn't all have to be the same thing. It could just be like, and it could be like the standard model plus like GR. Sure, there are some special cases like around black holes where like there has to be some kind of description that unifies them there, where it's like in this case this is what the properties are, sure, but there doesn't have to be some point where like all of the fundamental forces are the same. There's no reason that they all have to be one force. It doesn't all have to like integrate the same way that electromagnetism did. But I think that's still one of the leading questions, especially in the theory community. Of like, I know that a lot of people in theoretical gravity, for example, I asked them what they're doing on their thesis because they were saying, I mean, if someone solves like the gravity quantum mechanics problem or the quantum gravity problem, they're going to win a Nobel Prize. I'm like, so you can't be expected to do that for your PhD. And essentially, what they said is they generalize a different kind of problem. So space-time, the way space-time is curved is different depending on different models. And essentially what they do is they use a model that they know is wrong, and they try and explore different possibilities within that model. And they hope that one day when they find the right model, they can map the problems that they've solved onto the correct model. And that's their thesis. I always thought that was interesting and made me glad that I didn't end up doing quantum gravity because I wouldn't be happy about that. But like, I also go to their theses and I have no idea what they're saying, even though I'm in particle physics. I feel like they're speaking a
Oh
foreign
wow.
language.
Okay.
Yeah. So I see their work with a lot of admiration and maybe not the most amount of understanding. So I whatever it is, I think that's one of the problems in particle physics today, in addition to finding these additional gaps in the standard model.
Okay. And so you mentioned that you spoke with Frank Wilczek, who I'm just going to mention that I read his book Fundamentals recently, is Fundamentals, right? That I highly recommend reading because it goes through a lot of the topics we've been talking about today. So that's a good beginning if all of these concepts are quite novel to you. But this was on your Xapiens podcast, which you host at MIT. And so I wanted to know what got you into that, but also you've spoken with many incredible people on that podcast platform. What are the most interesting lessons that you've taken from it?
Yeah, so there's a lot of meat there. So yeah, I met with Frank Wilczek, which is a really cool experience. We Bobby and I, who's the co-host on the podcast, got to go to his house actually over in Lexington, and did a full interview with him there. That's all up on YouTube. And we've also had Ray Weiss on, who did gravitational waves, who won the Nobel Prize for LIGO, which was in the news a couple of years ago. And that was an awesome interview. He was super energetic. But how I kind of got started in Xapiens was I wasn't the actual person that started Xapiens. It was she was an undergraduate when I was a first year graduate student, I want to say. Her name's Sarah Noosh, and she founded this group that was devoted mostly to human enhancement and kind of transhumanism. And when I first went to graduate school, I was very on the cusp of working in particle physics or working in biotechnology. I had an offer to work with Ed Boyden, who I believe you either have interviewed
Potentially
or
will be soon.
are trying to interview. Who potentially will be soon interviewing. He's truly an amazing guy. Like there are a lot of people I've had on the podcast where I'm like, oh wow, like he has a Nobel Prize, and he's just like a regular guy.
I've spoken with him. He's lovely.
Ed was one of the few people where I was like, this guy he's different. Like he's special. He's a truly like brilliant guy. And so I had my opportunity to work with him or to work with my current advisor, who is also just a really amazing advisor, Janet Conrad, in particle physics. And it was a very difficult decision, but I ended up going into particle physics, but I still kept in touch with Ed, and still very much was interested in biotech. So when this group came along that Sarah Noosh started, and Sarah Noosh was actually in Ed's research group, I hopped on it and I became pretty deeply involved in it because I was like, this can kind of get my biotech itch while I'm in graduate school and while I have this great opportunity at MIT to talk to all of these random people who I otherwise wouldn't have been able to just kind of like knock on their door. So there were a couple other of us who have kind of like come and go throughout the years. And we started out giving talks at MIT, where we would have postdocs and professors come in and give a lecture to a group of students who wanted to show up, and then give people pizza and whatever. And then we had a big seminar series that ended up having like 1,000 people show up that had these like 5 big guns of George Church and Max Tegmark and David Sinclair and Ed Boyden and Patty Mays and Joe Paradiso. And that was a super awesome experience. And then after that, we kind of like we didn't really know what to do after that. And so we started giving more kind of like private seminars again. I led a seminar with someone that I had worked with at Draper, who did this like dragonfly technology, where it's basically like he kind of hacked into the neurosystem of a dragonfly and controls how it flies around with this like MEMS
Oh,
backpack.
interesting.
Yeah, it's a real wild one. But yeah, if you look up dragonfly with the I being EYE at the end, you'll find some of his stuff. So he gave a presentation. We couldn't post that one though because of like Draper
Oh, I
intellectual
see.
property
Okay.
issues. And we were about to do the book release for David Sinclair's Lifespan. And we had like posters set up and events set up, and we were advertising. And then like 2 days before, COVID kind of started to really get out of control, and we had to cancel it. Which I am kicking myself for now that it's become like a New York bestseller and everything. He had been showing us preprints. He was super excited for this event, and it got canceled, and then and then it ended up being a bestseller, and I'm like kicking myself because I was going to be like the host for it and everything. But then after that, we were all kind of adjusting to COVID for a while and being remote. Sarah Noosh ended up going to graduate school out in Stanford, which kind of broke up the group a bit. And then that was around the time that Bobby, who's the current co-host, came on and started to get more involved. And even though the podcast itself is drop my mic for a second. Even though the podcast itself has only been going for like a year, for probably like 2 years before that, we were actually doing interviews with professors, and we would essentially go over a paper or two. We'd have someone analyze it. We'd talk about it as a group, and we would always end up with more questions. I mean, that happens at the end of every journal club, where you read all of these papers and you think, okay, I think this is what they meant. I'm not really sure about their like methodology here. I'm not really sure how this works. And so we kind of leveraged the fact that we had this cool event and like this nice website to be like, oh, can we talk to you for an hour over Zoom and just like ask you about your research? And so we would do that, and we would have these interviews with like 5 or 6 of us and the professor, and learn all about their research and about their paper, and about what they were doing that might not have been public yet and stuff like that. And it was really cool, and we got to meet a lot of awesome people that way. And then Bobby sent me a link to Lex Friedman's podcast because he thought it would be cool, and I'd never seen it before. And I wasn't gonna watch it because it was like 3.5 hours long, and I was like, no. And I got sucked in. I watched the whole thing in a day, and I was like, well, you're sending me this link, Bobby. I feel like we can do this. Like, we're basically doing this already. We just aren't recording it. And so that's how it started. And we kind of pushed each other to do that. And it was, Bobby was huge, especially in the beginning. I was pretty low bandwidth, and he was able to. He built our studio. He found a lot of the equipment to purchase and figured out how to get it like funded through ASA, and really put a lot of it together. And so that was how the podcast itself got started, and I thought it was good that we had it just so that we had a record of all the people that we talked to, and that way, if we wanted to go for funding or if we wanted to talk to someone else, it's always good to be like, see, we've talked to these other people too. Like, we're not just making this up. We didn't just like have this random Zoom call that the person may or may not remember talking to a bunch of random students. Like, no, it is on record, 2 hours. Like, here, these are all the questions that we have. And at the same time, it was great for me because I got to learn about biotech from all of these people that are really intense in the field. And so I kind of do. I've said to some people that I do each interview like 3 times, because before I interview someone, I'm typically like, I look a lot into their research, I read their papers, I watch their other interviews and talks, then I give the actual interview, and then the third time I'm editing the video again, I hear it again. So like by the end of it, I've absorbed so much of that information that I feel like I've learned a ton of information about whatever subject that they were on. And so we tried to focus kind of on biotech because that was something that I really wanted to learn about. But then because we're in the physics department, we realized we're like, well, we can get these cool physics people to come on too, and just kind of like bug them because we know who they are and we're in the same department as them. And so that's how like Frank Wilczek and Ray Weiss and Joe Paradiso and a lot of these physics people have gotten involved. And then recently, we have an unreleased episode, hot off the press, that Bobby actually interviewed a rapper. I don't know if you ever heard of Lupe Fiasco.
I don't know.
No, no. One
I'm
of your
sure,
listeners will
yeah.
have heard of Lupe Fiasco. and but he was apparently some like visiting scholar at MIT, and Bobby got a hold of him. He had no idea who he was, but I did. I've been a fan of his for years. And then he's like, I came in, the question sheet had like Lupe Fiasco on the question sheet. I was like, Bobby, you got Lupe Fiasco on? How did you do that? He's like, I don't know. I just like emailed him. But yeah, so we're branching out a little bit in terms of just like all of the different people that we've had on. I mean, I got to talk to you on our show, which was great because I got to learn like what it's like as a biology grad student, which could have been me in another life if I had switched fields. And then learned about a lot of projects that I never would have understood otherwise. A lot of the organ on chip work that is done at Emulate that I talked to Donald Lingber about, I really loved. I thought that was some of the coolest stuff ever. And that's something that after I graduate is something I want to get more deeply involved in, because I think if you combine that with a lot of the things like the Yamanaka cellular rejuvenation could have like a very high bandwidth in terms of like research output, and I thought that would be really interesting. The conversation I had with Matthew Methelson was amazing, just from like a historical point of view, because he's been involved in so much, like being part of discovering mRNA, which is now like a household name. Like that's insane. The Methelson Sol experiment, which might not be like a household name, but is also like
a lot of.
one of the most
I'm pretty
important
sure most
experiments
biochemists
in biology.
know what that experiment is.
Right. And I mean, that's just like two of his kind of like getting to know you questions, where his main thing was like, oh yeah, I also did the International Bioweapons Treaty, and was like hanging out with Henry Kissinger. So that was a crazy interview, and I'm really proud of that one. And he really enjoyed it too. I was glad to hear later that he was showing it to his friends and family, which made me very excited that he liked it. Because sometimes we interview people and they really don't want to be there. Most people are good, they're polite, but a couple of times after the interview they just kind of leave, which isn't always the best feeling. So I was really happy that he was excited.
It was a really good interview. I do
Um,
recommend my viewers to watch it as well if you find the time.
Yeah.
But anyways, as you mentioned,
Yeah.
one of the reasons why I was keen to talk to you is that I feel like one thing I want to do more on my channel is to kind of demystify what it's like to do a PhD, because a lot of people don't realize what it involves, and also there's a lot of differences depending on the discipline, and even within like physics, like different PhD projects, as you've already sort of mentioned, can be very different. And so, how have you navigated your PhD process now that you're coming to the end of it? And you kind of alluded to it already, but what exactly is it you're hoping to do when you graduate?
Yeah. So, navigating the PhD process is kind of weird, and I feel like it probably definitely varies depending on school. In my case at MIT in the physics department, I was really lucky in that, and specifically actually in neutrinos and dark matter. The Literally like our neutrinos and physics, our neutrino and dark matter hallway is super nice and super supportive. And my advisor was also very supportive in doing things like my oral exam and making sure that I was prepared for that, and quizzing me every week, and like coming in on Sundays to make sure that I was like prepared. Even if I didn't want to come in on Sunday, she was there and she scheduled these meetings. And so having a support group, I think, is probably one of the most important things in graduate school, because the reality is that we've really, modern day has changed a lot in how education is done, because of the internet, because of science channels like yours, and what Xapiens is trying to do is give access to massive, like, these amazing resources and people that, like I said, I'm lucky that I can go and knock on these people's doors. And so by able to put these interviews on the internet, I hope that people can actually get some of this useful information that I wouldn't normally have had access to. And so with the way the internet has, like, you can find anything on YouTube now. Like I needed to fix an alarm system yesterday, and I was able to just kind of like YouTube it and figure it out. Um, right, like it's literally everything is on the internet, and that's changed even like the past 10 years, right? Because more and more content has been coming out. So in terms of an education, like going to different universities has, I feel like, has very minimal effect on your education, like raw, because for example, all of MIT's courses are
Mm.
online. MIT OpenCourseWare is all on YouTube. You can go to all of the lectures and get all of the course material that you need online. No matter, like, you don't have to have a bachelor's degree. You could be a high school student and you can
You
be
mean
taking
even
these
like the
classes.
notes? I mean, you
Um,
can watch the lectures, right? But you're saying that
yeah,
everything's on there?
everything's online. If you go to MIT OpenCourseWare, the lectures are all online, but they also have the notes, they have the homework assignments, they have the exams. Sometimes they don't always have the solutions for
Oh
them, but
no.
I mean, if you do Googling, I'm sure. No, but like you need to be able to grade yourself, right? You need to figure out like what the answers are. Um, so I mean, but all of the material is there. Like we live in an age where like you really don't even need to go to school to learn to go to
Yeah.
these classes. So what's the point, right? Like what's the point of going to these various institutions? And it's really like it's really the people you work with, um, because the ability to go and knock on someone's door or to text somebody who knows way more about this than you do is really what the valuable resource is. Because there have been so many times I have been so lost. like when I, especially in my first year there, it's like drinking from a fire hose. I had no idea what was going on, and it's really helpful to be able to go to someone and ask them what's going on and have them walk you through it, and physically be there to like go on the whiteboard and talk about each individual step as things go on, because science is hard, right? Like science is you have to learn a lot of things that are very complicated concepts, that a lot of the time are not made very clear in an hour and a half lecture and are not made very clear in a textbook that was written 30 years ago. So it really helps to have these individual people talk to you. And on the flip side, being able to help other people as well, because you learn a lot by teaching too, because you start to see, oh, I have all these little gaps in my own knowledge that I need to brush up on and understand. Um, and so I think that's definitely the most important, is to a lot of people, and I thought this was going to happen when I went to MIT, and I was pleasantly surprised that it didn't. A lot of people will try and isolate themselves and be like, I can do the problem sets all by myself. I can do this all by myself, and that was not the case. And I don't think people should do that, because I think human beings are a great resource, to be able to help you learn and to help get things done.
Yeah. I mean, that plus, I think people are always willing to help you. I mean, obviously, people can be stressed out one day or be too busy, but I think people generally want to help each other. Um,
Yeah, I think that's definitely true, and you see it a lot. I noticed it even when I was in high school. Sometimes helping someone is an ego thing. You're like, I can do this. Like I know this well enough that I can
mm,
teach it to someone else. And there's definitely like an element of pride to be able to explain something to someone else. Um, and also, especially, I've noticed it a lot at MIT actually, that it will bug someone if they don't know the answer. And so if you ask someone and they don't know, it's going to bother them, and they'll probably, and like I've asked someone a question, and then they didn't know the answer, and then I went and like tried to figure it out for myself, or I asked somebody else, and then they'll come up to me like 3 hours later and they're like, "Good, I figured it out." Like
I've been
this is
that
how you do
person.
it.
um,
Yeah.
yeah. So that's, yeah. I mean, I think it's interesting what you're saying. I find the same thing. Obviously, I can't, go and do my same process 10 years ago. Like I happen to have just done my education process in the time that we live in, but it is interesting to well, I also like, I'm always amazed at how much information is available for us to sort of like learn any kind of topic that you might find interesting. And again, like as you say, having a sort of platform to speak with people. I mean, scientists always like to speak about their research. It's always just amazing to hear and learn about different things. And so I've interrupted you again, but you were going to tell me about your next steps.
Oh yeah. My next steps. So before I came to MIT, I was working at a lab called Draper Labs, and uh, it's a DoD lab, non for profit, that basically works mostly on government contracts and Department of Defense work. but also branches out into biotech. And I found out this morning actually does organ on chip study, so that's something I might look into. They paid for my fellowship, so they're paying my tuition and my stipend while I go to
Do you have to
MIT.
pay for your PhD?
So, well, it's kind of funky. So, it depends on what the degree program is, but in physics, kind of the rule is you do not pay for your PhD. Someone pays for it. A lot of the time, it's an advisor. Sometimes it is a fellowship through the university, and sometimes it is a fellowship through some external source. A lot of the time, it's like the National Science Foundation is one of the more common ones. If you're in the military, then there's also a lot of military scholarships as well. And then there's these other like pseudo military entities like Draper and like Lincoln Lab that will pick out individual people and pay for their PhDs and their stipend. And so having that fellowship was actually really helpful for me, because then when I applied to MIT, I could say, well, I already have funding. You don't need to like take up the fellowship money from these other students. And I really think that helped my chance of getting into MIT as a graduate student. It at least like kind of put a blip on the radar of the admissions committee, to see that, oh, this is like, it's a free student. I'm free labor. Like, please take me tier 1 university. that was kind of the attitude. But I think that really helped and made a difference. I'm not committed to go back there. I probably will, because I enjoyed my time there. But there are also other groups that I think are really interesting. And I've gotten job offers from, like the VC. When I mentioned Donald Lingber earlier, the institute that he founded, the VC Institute, I thought was super interesting, and I might apply for a job there. And then there's Life Biosciences has some of the IP for cellular rejuvenation, and Altos Labs is another one that works a lot in cellular rejuvenation, which is something I wanted to work on after my PhD. But I don't have any experience in that, so I'll have to see if they'll even want to take me. But those are some of the options of what I'll probably be doing in the next couple of years. But I think I'm flexible to how that's going to go.
Interesting. Yeah, I mean, it's interesting as well that I feel like the further I've progressed into biochemistry, and like I guess the way that the way scientific research, at least in biology, is you get very focused and more focused on whatever it is you're trying to solve. But I kind of, one of the reasons I like doing the channel is that I get to talk and learn about other areas. And so physics is something that I've always did it like up to A level, and even slightly in my first year of undergrad. But then just, as soon as I chose biochemistry, it was like pretty much just like forget everything, just focus on biochemistry. And now it's something I'm kind of like, this is actually quite interesting and something I want to learn more about. And so it's interesting that you've kind of had a similar thing where you went heavy into particle physics and now have these other interests in understanding biology better. But given your expertise in physics, I've got just a couple of like more quick fire questions. Kind of like when I think of physics, what I
you asked all the hard questions earlier about like fundamental symmetries and like what are neutrinos and how does the standard model work. Those are all the hard ones. No, like how do magnets work? Like that.
Okay, yeah, but I think, I mean, there's a lot of interesting questions in physics, and so one of them, I guess it's more also related to computer science, but a lot of talk was about artificial intelligence and more AGI, artificial general intelligence. And I think for me, like the interest is, what are the timescales on these things, and how would that affect our futures?
So, I mean, I'm not an expert in AI or ML. I have one machine learning paper that was very niche in terms of accelerators. I do a lot of reading on it, but I mean, some people think AGI is around the corner. I don't know about that. There's some that I think probably the most exciting prospects is the stuff, not necessarily OpenAI, but a lot of the stuff that OpenAI is working on that has this idea of kind of a co-pilot. I mean, literally code pilot with their new product that kind of like helps you write code based on visual inputs. I think that's one. It keeps away from the fear of AGI, where it's kind of like people are still in the loop. But I also think it's probably going to be easier to do. The more autonomous, I think, I thought the other day, probably the biggest explanation of mastery is automation, right? So if you completely understand how to do a system, then it can be fully automated, which means it's really hard to fully automate systems in any kind of way, whether it be AI or even just like mechanically, right? Like in the old days, you had like physical automatons that you had to like understand each of the pulley systems to make sure that they could do something. But in AI, it's just as difficult. Like people are talking about having AI write novels or things like that, and that's GTP3 is working on that. But whenever you read a novel by GTP3, it's terrible, right? Because it's all over the place, and it makes sense for like a paragraph at a time, and then it turns into a disaster. I saw there was a thing in the news a couple months ago about some Google scientist who claimed that their Lambda computational model had
I
become
saw that
conscious.
too.
Uh, yeah, and it was immediately snuffed out by like everyone in the AI community. Um, and I actually read the transcript about it because I was very curious. And the things that got picked up by the news were the very typical annoying pieces that they're like, oh, it said it didn't want to be shut off. Oh, it said it was scared of dying. And I mean, that's like very common. I mean, we've had code that does that since the 90s. It's like if I say, do you want to die, say no, right? Like that's not a sign of intelligence. But there was something in the transcript that did really intrigue me, and no one talked about in any of the press releases, where he asked it to tell him a story about animals with like a moral theme. And it was a story about an owl, and then afterward he asked it to give like connections to what each of the characters represented, which is something I've never seen AI do before. And it was able to accurately describe the representations of each of the characters and even identify to one of the characters and explain why explain why it was able to identify with one of the characters, which I thought was really weird. I'm not saying that's consciousness, but I think that's something that hasn't been talked about at all in that transcript, which I thought was very interesting. Um, so you have groups like DeepMind that are basically trying to make AGI, and I think if that ever happens, it will be extremely revolutionary because now you can have kind of like free labor. Now you can just like copy print all these AGIs everywhere to be able to like replace graduate students. But so I don't think that's such a bad thing. I don't know how soon it will be, but I think it will make a lot of things easier and will probably increase our productivity.
Yeah. And then the other thing as well, like in terms of the energy that runs these things, obviously there's still a lot of talk and hope about nuclear fusion, which I guess to some extent does overlap maybe with your research or not.
So I share a lab with the fusion people.
So literally overlaps.
I'm in the what?
Literally overlaps.
Oh yeah. So I'm in the Plasma Fusion and Science Center. I'm on the plasma side because I have like an ion source that's about this big, and they're working on a massive reactor that's like the size of a building. And I get like one room, and they have like the rest of the building. But they but I can't see any of their stuff because it's all like proprietary and like very hush hush. I hear rumors swinging around there every once in a while. I know that recently Lawrence Livermore achieved ignition, but I don't think it was a super sustainable way. And there has been there's kind of like there's weird approaches to fusion because like we know fusion is possible and humans have achieved fusion. That's
With a
something a lot of people
tiny,
overlook
tiny.
is like, oh, we achieved fusion. Well, yes and no. We've actually achieved large amounts of fusion, right? A hydrogen bomb is a fusion bomb. Like we do fusion all the time, and a hydrogen bomb, you can even argue, is that like is an example of ignition. We have we have put in far less energy into a hydrogen bomb than the amount of energy that gets put out. And so there was talk for a while. I think some of it ended up becoming classified, and some of it was just kind of died out because it wasn't very practical. Of basically trying to find a way to use weapons like nuclear weapons as an energy source because that is a demonstration of how fusion can be done at ignition. And so that's one way, and that's somewhat similar to the way Livermore did it. Livermore used basically a ton of lasers and then fired it at this single pellet, and they were able to achieve ignition that way. But I don't know how sustainable it is. Like I don't know how many of those pellets they're going to be able to
Yeah.
use. I'm not an expert on that. and I don't actually know anyone on that experiment, so I can't ask. And then there's the people at MIT that are making a tokamak, which is basically this massive donut that makes a highly confined plasma. And the thing that people have been working on tokamaks for a long time, and they haven't been able to achieve fusion, but it's basically because they don't have a strong enough magnetic field to have the confinement tight enough. But now they have stronger magnets, so hopefully the confinement will be tight enough to achieve ignition. Um, I don't know where that's going to go. I've heard good things and I've heard bad things. I don't have any inside information. If I did, I probably shouldn't share it. Uh, but I really don't. Again, fusion is something that could be really amazing and could totally change like our energy footprint and the way that energy is achieved. But fusion has been 10 years away for the past like 50 years. So there's also a healthy amount of skepticism that I think goes
Yeah.
into it.
And so also you have a breadth of knowledge in this field, and so where is the best place or best resource materials? I know you've already mentioned the MIT Open platform already, but where can people go to learn more about physics or just explore some of these topics we've discussed?
So to learn more about physics, it depends on how deep you want to go. I think that's probably the biggest thing you could trip up on would be if you're a complete novice at physics, like watching my interview with Frank Wilczek might not be the best place to start because I start going in on like on field equations and stuff. That's probably not the best. Like that's probably like undergraduate level physics. If you're like a complete novice, then I mean, there's tons of other great YouTube channels out there. Like Veritasium was something that I loved when I was an undergrad. The coolest thing I ever learned about physics was from a Veritasium video, actually. And like Minute Physics, they're all these. What was the other one? Up and Atom. That's one I've actually been
I
watching
met
recently. Um,
the Jade who runs Up and Atom. I have,
you
yeah.
did? I wanted to get her. I wanted to
Oh,
get her
okay.
on
I
Sapiens.
can put you in touch.
She's great. She taught me things that I didn't understand. Like I think she's
She is
awesome.
no super friendly.
Um,
Yeah, I can put you in touch.
yeah, yeah. But yeah, there's a ton of content on YouTube. I personally think a lot of the time I've seen cartoons of like, Professor, I need help, and then they just kind of like sprinkle resources and like paper citations at you, and I've never found that particularly
Yeah.
helpful.
I always think, I mean, when people ask me
I
similar
feel
things for biology, I always say just go to like the sort of very fundamentals. Like, I guess even an element of maths you would need before you want to step into physics.
right. So like personally, that's why I like YouTube as a platform so much more because I find explanations on YouTube, especially nice ones with animations like your videos, um, are typically much clearer and easier to understand than trying to dig through every citation in a research paper because I get totally lost and I don't end up actually learning anything. And then sometimes or in textbooks, there are some very well written textbooks. Like when I was an undergrad, Resnick and Crane was an excellent textbook. That was the textbook that like changed my mind that textbooks could be useful. Um, and uh, sometimes they can be great, but a lot of the time they can be awful. Um, so I think find a resource that works for you and stick with that, and especially find something that like excites you and gets you interested. Because especially like when I was learning physics in undergrad, I think it was the beginning of my third year is where I really felt like I started to get it and it really all started to click. And I think a big reason for that was because I would get my problem sets done. And I'd figure out my stuff out, and I'd be like, "Cool, now I have time to do something that's interesting to me." And then I go and I watch like physics YouTube videos because it wasn't because like I needed to learn more physics, just because that was like legitimately what I wanted to do, and it was something that was interesting to me. And I think that's something that's really important to understand a concept that you want to do. Is you can't just like you can grind through it, and that's possible, and you can be strong-willed to grind through it, but it makes it a lot easier, and you're probably going to be much more likely to stick with it if it's something that you legitimately enjoy and you found an interface that like excites you and gets you very interested in it. And that for me, that was YouTube.
Yeah, no, I agree. I'm also always watching YouTube videos. Great platform. So obviously YouTube's where they can go to find out more about Sapiens, but where else can people go to find out about your research and yeah, the kind of things you get up to?
Check my LinkedIn. Like, I don't know. Like, I mean, our group has a website, but I'm not sure how well updated it is. I do. If you like look up my name on Google Scholar, you'll find a bunch of my papers, which will describe a lot more about my research. And that if you look at my name on Google Scholar, it will be very widely in range because I think I've said before, IsoDAR is, for me, has split off into like 6 different things. IsoDAR was originally a neutrino experiment. But then because of its application, it also turned into a dark matter experiment. It also turned into a potential for medical isotope development. It also turned into this like new way to produce accelerators and a new way to like couple low energy beam transports and new way to inject beam into cyclotrons. Like there's a lot of individual pieces that will be split out. So in terms of if someone is interested in particular in my research, they can also just like email me, lwaites@mit.edu. Like I'm not too afraid of getting spammed. If I do, then I'll figure that out. But if I get too many emails, I think that's a good problem to have.
So this whole time I've been speaking to a potential future Nobel Prize winner then.
Oh, I don't think so. I remember Freeman Dyson at one point too, who I would love to aspire to be one day. Freeman Dyson, even though he's like one of the fundamental people, not only in physics but also like in science fiction, creating the idea of the Dyson sphere, and also like being the real person behind Feynman diagrams. I mean, Feynman kind of like made his squiggles and whatnot, but Freeman Dyson was the real person that formalized it. Also a friend of Matthew Methelson, by the way. But Freeman Dyson never won a Nobel Prize, and when he was asked about it, he said, "There's like, well, I can't keep my attention on a single project long enough for me to ever get a Nobel Prize. I like to bounce around too much." And I agree with that. I get distracted way too easily, and that's part of why IsoDAR has split off into 6 different things, because I get distracted on different projects, and now I'm like, oh, I like longevity, oh, I like organ on chips, and that has nothing to do with my thesis.
Yep, I definitely
so I need to finish my thesis, and then I can start getting into these other additional projects. But I guarantee like 5 years down the line, if I'm working on organ on chips and longevity, I'm going to find something else that interests me, and I'm going to get pulled in that direction. So yeah, Nobel Prize winner, I am not.
Well, I wish you the best of luck with finishing off your PhD, and yeah, best of luck with whatever career path you decide to choose. And I'm sure we'll talk again in the future. It's been great, having you on the platform today.
Yeah. Thank you very much. It was great to see you again, Eleanor. So everything is a wave, but also a particle. But the thing is that everything, you can think of everything actually basically as a wave, but it's really, something's a particle, it's actually just a really, really tight wave. So when you talk about a double slit experiment, for example, and you look at the distribution patterns, if you look at the distribution patterns with fine enough intensity, you'll actually see with regular particles that you also will get an interference pattern. And people have done this up to things as large as buckyballs, actually. So when you talk about the Heisenberg uncertainty principle of like you can't understand something's position and momentum at the same time, it's not because like as soon as you see the position, the momentum goes away. They physically are not like they aren't simultaneously measurable. The reason why is because, and one example that you hear is that, oh, if you shine light on it, then it changes its momentum, and then that changes its position. That's not a good explanation. So a better explanation is, think of it like a wave. So say you have like, I'm standing here with a rope and I'm wiggling my wave back and forth. If I make really sharp peaks, right, and I whip it back and forth, I can say, okay, the position of the wave is just that one lump. And that I have a really well-defined position on that. But I don't really have a good understanding of its momentum because like I don't have its frequency. I don't have the energy that's traveling in that because I'm not able to describe its frequency. But if I do it a whole bunch of times, then it's super spread out, right? And you have all of these waves going around. And because you have all these waves, like all of these different like troughs and peaks and troughs through the wave, you can now get a good understanding of its frequency, but you have no idea what its position is because it's now spread over this large distance. And so the main thing with position, people are used to talking about position in terms of absolutes. That's like, this is this one individual piece, right? But position exists as as an integral. It exists between these two separate positions. And so as you shrink that down more and more, you get less of an ability to actually measure the frequency of an object, which means you have less of an ability to look at its momentum. So literally based on how they are defined, if you look at them from a wave perspective, that's what particle duality is. Particle wave duality is. It has nothing to do with, like, people say, oh, I made an experiment that can measure them both at the same time. No, by definition, you can't measure them both at the same time.
So it's not like an experiment. It's not like a technical experimental limitation. It's just by definition.
Yeah, and it's also not something that you can like out clever your way to do it. It is like it is a definitional thing that when like position and momentum have to be separated because of how we define position and momentum. It's the same thing with the eigenstates I was talking about before, the flavor and mass eigenstates. Like, you cannot simultaneously measure the flavor of a neutrino and the mass of a neutrino at the same time, because they exist as superpositions of each other. The mass is made up of a superposition of being all three simultaneously, the electron, the muon, and the tau neutrino. And the electron neutrino is by definition made up of the mass states of mass 1, mass 2, and mass 3 of the neutrino. And they cannot exist separately. They are by definition those three. They are superpositions of those three.